in my area where I'm residing, it is basically NCR. There is a cold wave for last 3-4 days, and I'm dealing with fever and cold and cough for last 7 days. I have already told Shamapad. But yes, I'm very much uh, excited to share my experience, my knowledge in technology, first of all, then my experience a little bit in the quantum cryptography domain for today. So let me share my screen. Am I able to share my screen, Shabada?
Yes, sir. Yes, sir. You can do.
Let me know if it is visible. Is it visible?
Yes, sir.
Yeah, perfect. So I'm just any time you can ask any question, just stopping me whenever I'm giving lecture in this particular session. And I'm just stopping my camera for ease of the use of the overall presentation. Please be free for asking any question or whatever you have in your mind during the lecture. No issue. Just just make me stop and then ask the question. No issue. Okay. I'm just turning off my camera and I'm turning on my presentation. Thank you. Okay. The introduction has already been given to all of you. No issue. Now, why this particular term, quantum safe cryptography? Is cryptography vulnerable today? First, we will deal with a very basic thing around cryptography. Who don't know about cryptography? I think all of you know a little bit, but we will go through. We will recap that particular thing. Then we will discuss why cryptography is in threat, why we need quantum safe cryptography, that is threat from quantum, and then we will discuss about what is the solution, what are the solutions actually for having a quantum safe cryptography. Okay, so classical cryptography, you all know that classical cryptography is basically about encryption and decryption. Whenever I want to send a message to anyone, then through a public channel, then I have to encrypt that particular thing so that if in that particular public channel, if anyone can retrieve that particular data, then he or she is not able to read the actual data or retrieve the actual data so that I have to encrypt it. In the other hand, whenever I'm receiving a data from a public channel, I have to decrypt that particular data because the data has been encrypted. And whenever I am able to decrypt it, then I can actually get the plain data or plain text, right? So in cryptography, we all know that in Latin, crypt means hidden. For this reason, cryptography is basically a hidden writing. Graphy is basically stands for writing. We know different kind of writing methods, different kind of languages for different kind of writing methods. So crypt means hidden, and graphy means writing in Latin. So whenever we are talking about cryptography, then it is basically means hidden writing. Now, as I told, we need two methods to do it. One is encryption. Encryption is basically the plain message or plain text has to be encrypted in such a way so that it cannot be decrypted easily. And decryption is the next method in the receiver end. Whenever I have to send a data from the sender end to receiver end, encryption has to be done in the sender end. And whenever the receiver will receive that particular data has to be decrypted. The method is called decryption. Okay. I'm going a little bit faster because it is very well-known thing to all of us. Now, there are two types of cryptographies are there. One is symmetric key cryptography and another is asymmetric key cryptography. In case of symmetric key cryptography, we have the same key for encryption and decryption. There are two methods I have already told, encryption and decryption. So we need key to unlock uh, and to lock. In the symmetric key cryptography, we need same key to unlock and lock the data, as we are using our traditional lock and key in our house or in our vault. The same key has been used for locking and unlocking. In case of asymmetric cryptography, we need two different keys. They are not symmetric, they are not equal or symmetric, whatever you can say. For encryption, there is a key which is not similar whenever we are decrypting that particular data. So at the time of encryption, whenever we are in case of asymmetric cryptography, whenever we are encrypting a data, we are basically encrypting that particular data with a key which is not same uh, as the key whenever we are decrypting it. So it's simple that we have different keys for encryption and decryption in case of asymmetric encryption. The example of symmetric cryptography is DES, 3DES, then AES, ES 128, ES 256. Different kind of algorithms are available for encrypting the data with the same key and decrypting the data with the same key same key used for the encryption. AES stands for Advanced Encryption Standards. There are popular two different AES techniques are available in the world, which are basically used for communication, encrypted communication or secure communication, you can say. One is AES 128 and AES, and the second one is AES 256. AES 128 is basically using a key of 128 bit length, and AES 256 is basically the algorithm which is basically use a key of 256 bit length. So these are symmetric cryptography. These are used for overloaded data communication. That means in these two categories, whenever you are thinking about symmetric cryptography and asymmetric cryptography, the symmetric cryptography is basically this symmetric cryptography is basically taking less overhead. Less overhead means less overhead. Less overhead means in terms of time and in terms of cost. Okay, but it is highly overrated in asymmetric cryptography. It is taking much amount of time, much more amount of time, and much more amount of cost in terms of space and computing resources. So whenever we are having overloaded communication, whenever we are having big data communication, we always prefer asymmetric cryptography. We will not prefer asymmetric cryptography. But it is required, very much required. I will discuss it later why it is required. This is the whole thing. Next, asymmetric cryptography. The example of asymmetric cryptography is RSA, Rives-Shamir and Adelman algorithm. Then Diffie-Hellman key exchange algorithm. Okay, so this kind of algorithm are basically asymmetric cryptography, which are basically use different kind of keys for encryption and decryption. These also are called public key cryptography. Public key cryptography. As you see that they have two different keys. One is public key, another is private key. Public key is used for encryption and private key is used for decryption. Okay. So two different keys are used in asymmetric cryptography. This is the RSA algorithm, as I told already. Then this is Diffie-Hellman key exchange algorithm, which is invented in 1976 with these two people. Okay. One thing I want to share that I have already worked with Adi Shamir, which is basically S of RSA on cryptanalysis after we have quantum threats on the cryptography. He is basically teacher, scholar, students of Wisband Institute at Israel. I have worked with him for a particular work for generating uh, a very secure key using a quantum device for different kind of cryptographic algorithm in 2019 end before COVID. I have personally met with him, and I have already worked a lot of work with him in that particular case. Okay. Now, the problem for this cryptography, these two cryptographic algorithms, that is symmetric key as well as asymmetric key, there is a problem. What kind of problem is this? The problem is basically the evolution of quantum computing. It is not quantum cryptography. The problem is quantum computing. There is an algorithm in quantum computing which is known as Shor's algorithm. Shor's algorithm. There are two very popular algorithms in quantum. One is called Grover's algorithm. His name is L. Grover. He is originated in India. He is Indian origin actually. And another scientist is known as Peter Shor from University of Waterloo. So there are two popular algorithms are available over there. One is called Grover's algorithm. Another is called Shor's algorithm. Grover algorithm can do a database search in a very faster way than the classical. Rather, it is faster than binary. The complexity of Grover's algorithm is basically order of root n, where n is the number of elements. Similarly, the Shor's algorithm is in another field, is working in another field. Shor's algorithm is basically able to factorize a large prime number in a large number in two different prime numbers in a very small amount of time, or you can say in a very faster. The complexity is basically over here is order of 1. The base complexity is order of 1. Obviously, there are some other operations are there. We have to add that particular thing. It is order of n, you can say, because we have to do it n times. Now, the thing is, large integer factorization, I can say large prime integer factorization is a hard problem to the classical system. Hard problem means it's NP, it belongs to NP. Okay, you know P problem, NP problem, polynomial time problem, non-polynomial time problem. So it belongs to NP problem, right? So it's a hard problem, and that particular hard problem can be solved by Shor's algorithm using a quantum computer. It is not about quantum cryptography. Okay, it is not about quantum cryptography. I'm talking about quantum computing. It can be solved using quantum computer using the algorithm called Shor's algorithm in a linear amount of time. That is, it can be solved in a polynomial time, which is basically a hard problem, which is non-polynomial problem for classical. But using quantum computer, it can be solved in a linear polynomial time, or you can say polynomial time. That is this, which basically turns the hard problem or the NP problem in classical can be converted in quantum computing scenario in a polynomial time problem. So it can be solved in a very efficient manner with with the availability of quantum computing, right? Now, the story starts in 1996. In 1996, Peter Shaw has developed this particular algorithm in quantum system at the University of Waterloo, and theoretically, he has proven that the integer factorization problem can be solved by his algorithm within seconds. I can tell you the actual data if still now we are using still now we are using RSA and Diffie-Hellman. These are the popular and benchmark algorithm. Diffie-Hellman. These are the benchmark and popular algorithm which are basically used for public key cryptography. As I told earlier, it is called public key cryptography or asymmetric cryptography, right? Public key cryptography or asymmetric cryptography, right? So RSA and Diffie-Hellman are the benchmark or popular algorithm for public key cryptography. Now, point is, these two algorithms are based on large integer factorization, large prime integer factorization, you can say. Because it was hard problem, I have already told, hard problem for our classical machine, classical computing devices, right? These are the hard problem for our classical computing devices. But right now, with the evolution of quantum computing devices from 2006, I can say, the algorithm has been proposed in 1996. The first quantum device, it is not quantum computer, but the first quantum device by D-Wave has been introduced in 2006. They are working on quantum annealing model. Quantum annealing model. It's a quantum device, but not quantum computer. After 10 years, in 2016, IBM has introduced their first quantum computer using quantum gate model, and they have introduced that particular computer in cloud called as IBM X. IBM X. These are these computers. There are two computers are available over there. These are 1 qubits machine. 1 qubit machine. That means only one computing unit is available, or you can say it's like bit. It's like bit. That means we have right now, say in my machine is basically a 2 terabyte machine, and it's a hard disk. But if you consider about RAM, that is random access memory, then my machine is 32 GB machine with its random access memory. That is which has been used for computation or processing. I'm not talking about register or processor memory. I'm talking about the random access memory. So like that, IBM has introduced in 2006. IBM has introduced a machine which is 1 qubit machine. Qubit stands for quantum bit. You can say it's the unit. Qubit is basically the computing unit for a quantum device. And today they have 400 plus qubit machines available with them. Okay. In 2023, after 7 years. Now the thing is, my point, the Shor, and obviously these qubits are not very much error free. They are erroneous. They have a lot of errors over there. They are erroneous qubit. So with these erroneous qubit, Shor's has to be solved by the source has to be solved with these erroneous qubits. Source can be solved, say with 1 million plus qubit. And IBM is targeting 1 million plus qubit machine available with them by 2030. So the thing is, these algorithms, RSA and Diffie-Hellman, who are popular, very much popular for public key cryptography, who are basically used in our banking system, financial transactions, e-commerce transactions, defense transactions, or any other secured systems. Those algorithm has been used as a benchmark and popular algorithm, and they can be broken tentatively by 2030 whenever IBM machine, 1 million plus qubit IBM machines are available, or 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 one more thing, uh, if we can reduce the error for the qubits, then 1 million plus can be reduced to 10,000s as well. So it is in between, you can say it is in between 2000, optimistically, it is in between 2028 and 2030. The all public key infrastructure, all public key cryptography should be replaced by something new, which cannot be broken by quantum algorithms. Till now it is clear or not? To anyone? Any question? Okay. So the thing is, this is a threat available with us with the quantum computing device. Now, whenever we are talking about quantum cryptography, we need to know a little bit about computing, and we need to know a little bit about cryptography, right? So I have told that this particular thing, that public key cryptography is available over there. It's a RSA algorithm. It can be electric car or Diffie-Hellman key exchange algorithm, which are popularly used, and that those algorithms are vulnerable using the Shor's algorithm. This is the first threat given by quantum. Now I'm coming to second threat. We have another kind of cryptography available with us, which is known as symmetric cryptography, right? Where both the keys for decryption and encryptions are same. For this kind of algorithms like AES, Advanced Encryption Standards, AES 128 or AES 256 or SHA, Secured Hash Algorithm. This kind of algorithm are basically using the same key for encryption and decryptions. For the heavily loaded data, whenever we are using, whenever we want to communicate heavily loaded data, we always use AES or SHA. These heavily loaded communications, whenever we are using this, then we are basically using symmetric key algorithm. Both of them, AES and SHA, both of them are symmetric key cryptographic algorithm. They are vulnerable to another popular algorithm for quantum, which is known as Grover's. I have already told. It is not able to break, see, public key cryptography, it can be broken, simply broken by Shor's. It has to be replaced. And symmetric key cryptography. Yes, please.
చేస్తాడు నేను ఓపెన్ చేయలేదు
Sorry?
ఏం మెసేజ్ చేశాడు?
Any question? I'm not able to understand.
Are you free that time?
Hello, please mute your mic if you are not having any question, please.
1990 Friday.
Okay, I think.
Sir, please go ahead, please.
Yeah. So, in case of symmetric cryptography, the key strength has been converted to half of the key strength using the algorithm called Grover's. Here you can see that it is basically it is vulnerable to the Grover search algorithm, and for this we have to mitigate this particular risk by increasing our key or hash. In case of AES, it will be key. In case of SHA, it will be the length of hash. Okay, so these are two threats, but the main threat is that the public key cryptographic algorithm like RSA or Diffie-Hellman, which are popularly used in all of our secure communication, like uh, whatever I am talking right now in Teams channel, that is also secured, and that is secured by one of these algorithms, RSA, Diffie-Hellman, DSA, or Elliptica, right? Whatever the transaction you are doing in your HDFC Bank, State Bank of India, Punjab National Bank, whatever it may be, there has to be a public key cryptography algorithms available over there, which is basically secure your communication in the very initial stage. Now, my point is, I want to tell you one thing in my explanation. I will tell you one thing that, see, uh, uh, there is a there is a there is an user called Mrityunjay, say, and there is a user called Shamapada, say. We want to communicate. We want to communicate some data between us, which has to be secured. Both way communication, no issue. We have the normal logic is we have to use symmetric cryptography. Why? Because it is with less overhead. Overhead, I have already told. Overhead means it's in terms of cost, in terms of time, in terms of computing cost, in terms of time, less overhead. So we have to use symmetric cryptography. No issue. But whenever we are using symmetric cryptography, we have to have one constraint. What is the constraint? Constraint is we have to have the same key. I'm writing K over here. We have to have the same key with us for encryption and decryption. So we need the same key with us. Mrityunjay and Shamapada both need the same key to encrypt or decrypt, whatever it may be. I don't know who is sender, who is receiver, right? And we have to use it. Why? Because it is less overhead. It is consuming lesser amount of resources. It is consuming lesser amount of cost. It is consuming lesser amount of time. Now, how this key can be shared? It is not possible that I am writing a letter that Shamapada, this is the key, and sending that particular letter to Shamapada. Whenever Shamapada is receiving that particular letter, then we will start communication. It is not possible. Here actually comes another kind of cryptography, which is known as public key cryptography or asymmetric cryptography. This public key cryptography generally used to share this key between Mrityunjay and Shamapada, or you can say receiver and sender. So whatever the communication, whether it is symmetric cryptography communication or simply public key cryptography communication or asymmetric cryptography communication, you always need public key cryptography over there to initialize the communication. That is my point. So it is very much important to create an infrastructure of public key, which is known as PKI. You can search Google. PKI is basically an industry today, which is basically providing the public key for two-way communication. To initiate two-way communication, it is known as public key infrastructure or PKI. So this is why I'm telling this, because I have to make you understand that yes, still we have another kind of cryptography which is not broken, which is only vulnerable to an extent. This particular public key cryptography is required to initiate the second kind of cryptography, which is known as symmetric key cryptography, to exchange the key between the sender and the receiver. At least we need at least once for the communication whenever it has been started. For one session, one PKI initiation is actually required to exchange the key between sender and receiver, and then we can communicate with the symmetric key cryptography, no issue. But it is required always, always. Now my point is, this is in threat. This is in threat by quantum system using an algorithm called SHOR, developed by the scientist called Peter Shor. Right. This is the scenario actually. If you go through the symmetric cryptography, then these are very popular cryptographic algorithms which are used for different kind of communication, and these are the key strength has been reduced by the threat created the algorithm by the threat created by the algorithm called Grover. It has generally going to be half for all the algorithm, all the symmetric cryptographic algorithm, whether it is AES, whether it is SHA, whether it is SHA 256, whatever it is. And if you go through the asymmetric cryptography, like RSA, ECDSA, then AES 256, I have already told these are symmetric cryptography. These are asymmetric cryptography. They are all broken theoretically by Shor. We are not able to break it in the runtime because we don't have a quantum computer device which has more than 10,000 qubits available with us. Whenever it will be available, then all the PKI algorithms like RSA, Diffie-Hellman, ECDSA, all can be broken within a fraction of seconds. I can give you an example which can be calculated mathematically for a 1048 bit RSA encryption. To break it, gigahertz capacity supercomputer will take 3 to the power 17 trillion years. Trillion years. I'm talking about years. It will take trillion years. A gigahertz capacity supercomputer will take 3 to the power 17 trillion years to break a 1048 bit RSA key. Sorry, 2048 bit RSA. It should be 2048 bit RSA. 2048 bit RSA. And for the same key, a megahertz capacity quantum computing device will do it within less than 10 seconds. So this is the threat we have in our current cryptographic system. And these all are used. These all are used in your banking system, cybersecurity, secure communication, defense, whatever it may be. Because I have already told these are required. We cannot communicate with only AES or the symmetric key algorithms. We need to exchange our key using Diffie-Hellman or RSA so that we can initiate the communication using symmetric key. So we always need this kind of asymmetric key algorithm to exchange our initial keys to set up the communications over there. We always need, and it can be broken less than 10 seconds using a megahertz capacity quantum device. Till now, anyone has any problem? Sorry. Okay, so let's move on to the next part. Now, these are the timelines. It is not started. Right now. Rather, it has been started quite a few years back. NIST is basically National Institute of Standard and Technology. It is the standard and it is basically backed up by Department of Commerce, Government of US. You can go through it, their site. They have already started to counter these particular threats by Shors and Grovers. Initially, Shors to encounter or how it can be done so that all the security system can be secured whenever the quantum computers are available for computation. So they have started it in 2016. Then they have launched. Okay. Let me go through this slide. It's 2016. Then they have asked for proposal. Then near about 82 proposals has been submitted in 2018. Then there are different kind of what kind of proposal I will tell you later. Then they have already gone through different kind of verifications, validations with all the proposals. Round 1 selected 69 proposals. Then they have initiated second round of proposals over there. Then in 2022, third round of proposal has been given, and in 2023 here, 2023 between 2023 and 2024, there are 4 algorithms among these 82 proposals. Only 4 proposals has been selected. It is given by CDOT, Central Department of Department of Telecommunication, I think, CDOT. So in 2023 they have already reviewed that, and in 2024 they are going to finalize the standard for the quantum safe communication. There are 4 proposals has been accepted, and there are 4 algorithms are available over there. 4 algorithms are available over there. 4 algorithms in 2 different sections, you can say, 2 different sections. One section is called KEM, key exchange management, or second section is called digital signature. Digital signature. For these 2 sections, one algorithm has been selected, or one algorithm has been passed. All these 4 proposals over there, one algorithm has been passed, and that particular algorithm is known as Crystal Kyber. Crystal Kyber. Okay. Coming to this point, Crystal Kyber. And for digital signature, there are 3 algorithms has been selected. One is Crystal Dilithium, another is Falcon, and another is Sphinx. Sphinx Plus right now. It is now named as Sphinx Plus. What these are? See, I have already told that in PKI or publicly current PKI, there are different kind of popular algorithm like RSA, Diffie-Hellman. So these kind of algorithms are available, but all of them are basically based on large integer factorization, right? But there are different kind of publicly cryptographic algorithms were available from the very beginning, which are hash based. Which are hash based, which may be code based, multivariate, lattice based, and isogeny. Now the thing is, among these 5 broad categories algorithm, there are 82 algorithms or 82 proposals has been given among these 5 categories. These all are used for public key encryption and public key decryption. Sorry, private key decryption. Public key cryptography. They are used for public key cryptography. Okay. Or asymmetric key cryptography, you can say. Now, among these 5 kinds of algorithm, total number of proposals has been submitted in 2008 was 82, and only 4 has been passed all the tests, or all the you can say all the benchmarked value over there. They are mainly, I have already taken it bold. I can also write it in different color. No issue. They are Crystal Kyber, Crystal Dilithium, Falcon, and Sphinx Plus. These 4 algorithms have been selected in the last round in 2023, and the benchmark has to be set in 2024. You can go through the site of NIST. You can find that these algorithms are available which are quantum resistant. That means quantum computer doesn't have any algorithm so that they can break Crystal Kyber, Crystal Dilithium, Falcon, or Sphinx, or any other classical computer cannot be available over there in the world who can easily break these 4 algorithms, and they can be used for public key cryptography or asymmetric cryptography for exchanging the key, for key exchange. Okay. So the point is, there are two things are available with this. So if there is a threat by quantum, there is a threat by quantum, there is a threat by quantum. To mitigate that particular threat, we have two different weapons. One is two different way, we can say. One is classical way. Sorry. For that particular threat, I'm writing over here. For mitigating that particular threat, we have classical way. And another thing, we have quantum way. So whatever I have told, like these algorithms, which are available, like crystal Kyber, crystal dilithium, Falcon, and Sphinx, which has been selected in the final round for public key infrastructure (PKI) and for digital signature. For public infrastructure, only one algorithm has been selected, which is known as crystal Kyber. And for digital signature, we have three different algorithms available with us. Two are lattice based, crystal dilithium and Falcon, and one is hash based, which is Sphinx plus. So these algorithms are classical algorithms. These algorithms are classical algorithms. So these are the classical way to resist the threat by quantum. And this kind of initiative is called post-quantum cryptography, PQC. Again, you can search Google, you can find there is PQC or post-quantum cryptography available, who are basically quantum resistant classical cryptography, where quantum cannot do anything with their algorithm like shorts and groves. So NIST or you can say Department of Commerce, Government of USA are basically trying to change the overall PKI, whatever I have given over here, which is actually required always, PKI, this public key cryptography. They want to change the PKI from RSA or Diffie-Hellman to crystal Kyber. And for digital signature, it will be crystal dilithium or Falcon or Sphinx plus. So they want to change the overall algorithm over there in overall public key cryptographic domain, and they want to change it to different kind of other public key cryptographic algorithm, which are known as, or which has been selected already 2023 by their development phase, that is crystal Kyber for PKI, and for digital signature, that is crystal dilithium, Falcon, and Sphinx plus. Any question till now? Sorry. Okay. No question. So we are going to the next phase. Next phase is the way. Okay, these are the initiative in different continent, different country for developing these algorithms, crystal Kyber, dilithium, Falcon, and Sphinx. One is called PQC crypto, PQ crypto, post quantum crypto, crypto math crest, safe crypto, post quantum standardization initiative. From different countries available over there. They are from Japan, they are from EU, that means European Union. These are from Crest, Cryptomath Crest is from Japan. There are some organization from EU, that is European Union, and some organization from USA. So there are different kind of organizations who are basically you can go through it. You can just write PQ crypto. You can find all the information over there. Safe crypto you can find. These are for Japan. These are for Japan. Japan is basically leading this particular way along with USA. Okay. The next part, what I want to tell, that is this way. Quantum. How to tackle this particular threat which is available for our classical cryptographic algorithm, not in a classical way, rather in a quantum way. For this, we have, uh, yeah, for this we have a particular concept which is known as quantum key distribution. Rather, exchanging the key, exchanging key means what? There is a sender, there is a receiver. Whenever sender wants to send a data to receiver, first sender will exchange the key to receiver. Then using obviously public key cryptography. And then the communication will be done using symmetric key cryptography with this particular key. This is a simple thing. Key exchange algorithm is basically exchanging the key only, then they have no work over there because symmetric key cryptographic algorithm are basically secure the communication with the same symmetric key. Rather, exchanging the key, quantum has some potential to distribute the key between sender and receiver. So there is a QKD device, quantum key distribution device. There is a receiver and sender. QKD is basically sending keys to sender as well as keys, the same key to receiver in a secure way. This particular technique is called quantum key distribution, or in short, it's called QKD. This QKD is basically built on two different principles of quantum principle, quantum physics or quantum mechanical principle, you can say. Quantum physics principle or quantum mechanical principle, you can say. One is called quantum teleportation, this one, and another is called no cloning theorem. No cloning theorem. No cloning theorem. These are two very critical concepts to explain at least quantum teleportation with 2-3 hours of 2-3 hours of discussion, so that I can make you understand how quantum works, how a quantum gate is working, what is Bell state, how quantum teleportation works, and different tough terminologies are available over there, but they are not actually tough if you can understand. But it will take time, so I'm not going that deep over there. But I want to make you understand that these two concepts, that is, first, teleportation, and second is no cloning theorem. No cloning theorem. What are they actually? See, let us consider there is a QKD device. I'm talking about in a very layman's language to make you understand. And there is a sender over here, and there is a receiver over here. Now, if I want to send a qubit to sender to put a data or to send a data over here, we obviously need a qubit, right? And simultaneously, if I want to send the same data to the receiver, data means actually which is key in both the case, which is a part of key or key, you can say, right? So we need a qubit. Qubit is basically again the same thing. I have already told bit in classical, the same thing in qubit, but they behave in different way. Okay. So I need to send two different qubits to sender and to receiver with same value. That means if the qubit has 0, then this qubit is also having the value 0. If the qubit is having the value 1, then this qubit is also having the value 1. Now, if I am looping it between sender and receiver using this QKD device, then sometimes I am sending 0 to sender. Sometimes in the same time I am sending 0 to receiver. Sometimes I am sending 1 to sender. and in the same time I'm sending 1 to receiver. Then again 1 to sender, 1 to receiver, 0 to sender, 0 to receiver, 0 to sender, 0 to receiver, 0 to sender, 0 to receiver, 1 to sender, 1 to receiver, 1 to sender, 1 to receiver, 0 to sender, 0 to receiver, 1 to sender, 1 to receiver. So it is basically forming a key which can be distributed from quantum key distribution device. This policy, whenever I want to send, if I have to, if I can able to send the same data with the same qubit, with a single qubit to sender as well as to receiver, then then these are basically creating the key, and this sending data from one place to another, quantum data from one place to another, you can simply say it's called a teleportation. I'm giving a very generic definition. I'm not going too much mathematics, too much physics. Okay. And the next thing is called no cloning theorem. No cloning theorem means no cloning theorem means what happened? Yes, no cloning theorem means if sender has read the data, say a qubit is basically taking a value called 0. Whenever sender has been read the data, then this qubit, the state of this qubit is going to collapse. It will be collapsed. Sorry, it will be collapsed. Okay. That means you cannot retrieve that particular data again. So we all know that, say we have a memory space, say memory 1. There is a value called 1. I can copy that particular value in memory 2 in another memory, and I can have that particular value over there. This thing cannot be done in quantum. That means you cannot copy a quantum state to another quantum bit. That means if you have a qubit, say called Q1, and you have some value over there, then that particular value cannot be copied. In classical, it can be copied, but in quantum, it cannot be copied to that particular step. Yes, you can obviously copy that particular value, but it will always move. That means whenever you copy that particular value, this particular qubit will be collapsed. So you cannot clone a value from one qubit to another. For this reason, whenever this QKD devices are sending data to receiver and sender and receiver, then if someone is want to read that particular value in any case, read that particular value, then that particular state is going to collapse, and the sender and receiver has been will able to know that yes, this particular value has been disrupted in between. So if some eavesdropper is basically want to listen that particular value in between in the channel of quantum key distribution, then it can easily be tracked that yes, this particular value has been tampered, this particular key has been tampered, and we can discard that particular key over there. So there are two different policies or two different quantum mechanical phenomena are available over there. One is called teleportation, another is called no cloning theorem. These two phenomena together is basically building a technique which is known as quantum key distribution, by which the quantum key can be distributed between two parties in a very secured manner without quantum threat, so that the key can be exchanged between sender and receiver, and they can communicate with the symmetric key cryptography, whatever we have in the classical system. So it's look like there is a QKD system. Here is a sender. There is a receiver. They are basically, the key has been distributed by the system, the same key, using quantum channel. I'm writing QC, quantum channel, and then whenever the key has been received by both the sender and receiver, then using the classical channel, the sender and receiver can communicate using symmetric key cryptography. And symmetric key cryptography is not totally vulnerable by the quantum threat. As I told, the key strength has been reduced. If we increase the key strength for the symmetric key cryptography, then they are having the same strength over there. So depending on the number of keys or depending on the size of keys, the symmetric key cryptography is not actually vulnerable to the to the recent quantum threat available with us in a PKI. So this is another method by which is basically a quantum way to to exchange the key or distribute the key between sender and receiver so that they can communicate with the existing symmetric key cryptographic algorithm like AES 128 or AES 256 so that they can communicate securely. Okay, so this is basically an algorithm which is known as BB84. This algorithm is known as BB84 algorithm. BB84 algorithm. This algorithm is basically used for this one, for distributing the keys between Alice and Bob. I can give you an example of B92. Yes, you can see it. Okay, so here you have sender, that is Alice. Here you have Bob, that is receiver. Sender and receiver are available over there. Now, how quantum key distribution is basically going to happen over there? Nothing else. Alice has a quantum. This is basically a quantum channel. The blue line is basically a quantum channel. This is the quantum receiver in the right side with the Bob, and these are the polarizer, because we all know quantum particle like electron, photon, they has different kind of polarization over them. These are the polarizer. So I'm taking a random polarization and I'm putting single photon over there. So Alice is basically sending single photon. If Bob able to receive it, then Bob is basically measuring that particular thing. Okay, simple thing like this. Again, Alice and Bob both are having different kind of randomization, polarization. Okay, I'm putting continuous over there. Show key generation, show key bit, and show total error. So you can see that this polarization is basically going to be random. The polarization from Alice to Bob, both are random. Bob is receiving each and every photon, and sometimes they have matched, sometimes they don't have matched, depending on different random polarization. Okay, so you can see that here Bob detected or not, or Bob detected or not. If detected, then Bob is basically storing that particular data and sending that yes, I'm detected. Bob is not telling that what I have detected, but Bob is basically sending a message that yes, I have detected your whatever you have sent. Okay. So, for example, here only one, the next one has been detected. Okay, like this. So I'm forwarding for 100 photons. This many of photons has been detected. Okay, you can check. So this many of photons has been detected. And if you find an error, then you can see that there is no error available with it. Whatever the key has been generated by Alice, that particular key has been generated by Bob. Okay. Now the thing is, it's a typical mathematical, diverse and tough calculations over there, because you have to know about what is Alice polarization. You have to know about what is Bob's polarizations. There are four different kind of polarizations are there. You can check over here. Alice polarization has horizontal 0, 1 and plus 45. Bob polarization is vertical 1, 0, minus 45. So the different kind of polarizations they are using. Whenever they are basically matching with their data, then then Bob is sending basically, yes, I have received your data. Then only that particular data has been fixed. So near about 25% data has been missed over there, or you can say 25% photon or qubits, whatever Alice sent to Bob, that has been missed over there. And after a certain period of time, whenever the total length of the key has been achieved, then they are basically stopping the Alice is basically stopping sending the photon to Bob so that Bob can receive that particular data. But it is very nominal amount of time. Within nanosecond, you can send, say, you can say for 10 MB data from Alice to Bob within a second. That means 10 Mbps data you can send from Alice to Bob, because they are using quantum channel. Quantum channel is basically photonic channel, so the communication is very much faster. So this is an example of quantum key distribution, which are basically the quantum way. To cut the long story short, my point is, my point was from the very beginning, my point was classical cryptography is in threat because of two quantum algorithms. One is called Shor, another is called Grover. This is Shor and Grover. Shor is basically targeting the public key cryptography, which is based on large integer factorization. And Grover is targeting the symmetric key algorithm, which is not broken actually, but vulnerable. They are basically minimizing the key strength of a particular algorithm using it. We can actually minimizing this key strength of the algorithm like AES or SHA using Grover. So it is not an actual threat. If we can increase the key strength, key size of AES or SHA, then there is no problem with that. But yes, this is a really significant problem for our classical cryptographic system, because I have already told that this particular cryptography is always used whether it is symmetric key or asymmetric key actually, because asymmetric key has been always used for initiation of any cryptographic algorithm for key exchange. So it is in threat. Public key infrastructure or public key cryptography is in threat. So there are two different kind of approaches available over there. One is classical way, which is known as quantum resistance cryptography, and another is quantum cryptography, which is built by quantum. And in case of quantum resistant cryptography, it is actually the classical cryptographic algorithm which are not vulnerable to the quantum threats like Shor and Grover. In case of quantum resistance cryptography, these are also called post-quantum cryptographic algorithm or PQC, which are again classical algorithm. So we have 4 classical algorithms after a lot of experiments, a lot of proposals, discarding of the proposals, experiment. Then we have reached in 2024. We have reached in last 4 different classical algorithms which are quantum resistance right now. The first one is crystal Kyber, which are basically used in public key cryptographic infrastructure, public key infrastructure or PKI, you can say. And other 3 algorithms, crystal dilithium, Falcon, and Sphinx. All these 3 algorithms are basically used for digital signature algorithm, or you can say DSA, digital signature algorithm. And then these are 4 algorithms has been shortlisted, and the benchmark of these algorithms has to be set in 2024 by NIST, US Department of Commerce. These are the classical way. Another way is there for having quantum safe cryptographic system, which is known as these are the initiative for post quantum cryptography, who are basically developing the algorithm. Another way is basically quantum cryptography. The main thing in quantum cryptography is basically quantum key distribution. This quantum key distribution is basically based on 2 different notions of quantum mechanical phenomena. One is quantum teleportation, and another is quantum no-cloning theorem. I have already discussed what is no-cloning theorem and what is teleportation is. Teleportation is basically send a particular qubit from one distance to another and keep a qubit over here so that both of them can possess the same value or they are behaving correlatively. No-cloning theorem is that particular theorem where you cannot copy a value of a qubit or a phase of a qubit or a state of a qubit to another qubit. Whenever you want to copy it, it is basically not copied, it is moved, because the first qubit from where you are copying, that particular state of the qubit will be collapsed or destroyed. So you cannot copy, you cannot have the copy of that particular state to another qubit. It cannot be cloned. For this reason, it's called no cloning theorem. Based on these two properties, we have quantum key distribution, which is basically the base of quantum cryptography. I've already told how quantum cryptography is basically working. They have different kind of polarization. Alice is sending different kind of polarization. Bob is receiving that. Based on that, they are matching their keys. Whenever the key has been matched with that particular key, they can communicate with different kind of AES or DSA or symmetric key, sorry, AES or AES 128 or AES 256 or different kind of symmetric key quantum algorithm with the classical channel. So key exchange has been done by this QKD. It is called Q distribution, not key exchange, because it has been distributed from the QKD device. And the last thing is, sorry. And the last thing is what we have developed in HCL with the collaboration of University of Calcutta, because we have already collaborated for last 1.5 years. We have created a quantum random number generator for securing the quantum keys for quantum device as well as the classical device. We have already filed a patent, US patent and Indian patent over there. We have a product called QNAS, which is known as Quantum Number as a Service, which has already been published in Amazon Web Service as well as Microsoft Azure Web Service. Microsoft Azure, you can say, Microsoft Web Service. We have two different publications. One is called QRNG. It has already been given for review to ACM, and we are going to submit another publication which is known as QSKE, Quantum Safe Key Exchange, which is also based on a hybrid approach of quantum random number generator, QKD, and post-quantum cryptographic algorithm. We have already developed in different vertical. We have already developed another publication which is known as QDLC or Quantum Development Lifecycle. It is nothing but software, one of the software development lifecycle, but in a quantum way, because there is a lot of changes over there in quantum rather than the classical. And we have also developed some small product in QML and QAI. QAI means quantum artificial intelligence and quantum machine learning, which are basically used in HCL own software category, which is known as AI on. AI on is basically AI development cycle platform. We have already created some quantum modules over there, and which has already been plugged in to enhance their services to HCL's client. So that's it. Any question from anyone? Thank you. Any questions from anyone?
Participants, do you have any question, please? Okay, I think nobody has any question, any queries. So, sir, actually, I am also starting this field. I have introduced one course here, a UG and PG level, and at the same time, I'm conducting this online course. So I have a interest actually mainly for that I have started it. What are the scopes of like apart from this post-quantum cryptography? What are the other scope of this quantum technology? Okay, for other problems, related problems.
Okay, for the short term, for short term, as the cryptography is in threat, for the short term, within 2 to 3 years, you can have a huge requirement for post-quantum cryptography as well as quantum cryptography like QKD, as I mentioned. And after 3 years, say 3 to 5 years range, you have a huge requirement in industry as well as in different organizations. You will have huge requirement on quantum machine learning and quantum AI for solving different kind of hard problem like vehicle routing, traveling salesman, then hand colony optimization, then material discovery, then material discovery in pharmaceutical, material discovery in electric vehicle, like creating battery optimization to do the battery optimization. Then you have the problem like protein folding to create vaccines and other drugs. Then you have weather forecasting. So different industry has different kind of problems are available. Energy, then you have pharmaceutical, then you have life sciences, then you have logistics, then you have defenses, then you have banking and finance for portfolio optimization, banking and finance. So different kind of hard problem can be solved. This is the second phase of this quantum journey. At the last phase, maybe after 8 years to 12 years, then you have quantum simulations. Quantum simulations is basically simulating a living body or simulating a natural body using a quantum system. That means, say you want to simulate some doctor want to simulate some patient's gene. So using quantum device, you can create the replica of that particular gene, and you can read the behavior of that particular gene in a natural way. How this particular gene can work, or you can simulate a particular molecule to check what are the behavior in different kind of weather scenario or weather conditions, so that you can previously determine that yes, this particular precautions can be taken for this particular device which is created by this particular material. So this kind of, so there are different phases are available over there. Right now, since it is already in threat, it is already, you can check that I have already told about NIST. You can check that it is 2026 is the deadline. All the banking system, financial system, e-commerce, wherever the security, cyber security is related, whoever using PKI, public key cryptography, they has to shift to post-quantum cryptography and QKD devices. There is quantum safe devices. So this is the first wave. The second wave is quantum AI and quantum machine learning, and third wave you can say quantum simulation. So more or less 4 years you can take, 4 years, 4 years, and 4 years. The 12 years journey you can have ahead for development or creating new theories, new applications.
So, as per your suggestions, what I understood, that if the new generation, in the sense the young people who are doing graduation and all, if they have like done quantum computing course along with knowing some tools, okay, writing codes and all, mainly for cryptography implementation and machine learning and all, so they will be having scope in quantum related job also.
Yes, you can go through LinkedIn, you can go through Naukri, you can see that the quantum related job is basically increasing in an exponential way. The company like IBM, Microsoft, Amazon, the big four IT like TCS, big four IT in India, that is TCS, HCL, Wipro, and Infosys, they have already created their own team. Say 2 to 3 years back, and they are expanding it. Then you have some new player like LTI Mindtree in our country, LTI Mindtree. Then you have Emphasis in our country. In abroad, you have Accenture, Capgemini. They all are recruiting quantum physicists, quantum computing. Initially, they were hiring quantum physicists only, say 2 to 3 years back. But right now, they are focusing on quantum computing people, quantum mathematicians. Except this, those people who are developing devices like the company like Rigetti, INQ, then you have Cambridge Quantum, the IBM itself. They are also hiring different quantum computing people or quantum software people who are basically, because they have already developed the hardware, right? So they want to create a layer of software over there to having different kind of service. So they need quantum software developers over there or quantum computing people over there who are basically create that particular software layer to give the solutions for the applications which are required high speed computing, super high speed computing from the quantum device. So they are, even if you go through different kind of job portal, you can find that yes, it is increasing exponentially.
Okay, sir. Thank you for your nice talk and your kind present. So actually, I appreciate. Apart from you have health issues and all, still your commitment I appreciate because you have given a lot of effort for preparing the slides and
Shahu has some question, I think.
yeah. So please. How you have any question? You raised your hand. Okay, I think Satyajit, you are having any questions, Satyajit?
Yes, sir. I have one question. For example, I'm computer science background and I am having some experience in IT. And I want to shift to quantum computing field. So, what way I should proceed? I mean, I have gone through few course and like Udemy, and then going through all lectures, but somewhere gap is there. So, how you are suggesting to enter into this field in a good way?
Okay. The first thing is that for entering in quantum computing field from a computer science perspective or computer science students perspective, I would suggest you to first read about very basic principles of quantum mechanical principles like superposition, entanglement, no cloning theorem, decoherence, and interference. These five principles you have to understand first in a very basic way. It's very simple, and it will take maximum of 2 to 3 weeks to understand it. Not very much mathematically, but in a very you can say very theoretical way, not in a
Yeah.
mathematical way. Then you have to understand how these principles can be mapped in quantum mathematics, and then how can it be transferred to quantum computing. So you need the basic mathematics behind these five principles, how this uh, concept can be converted to quantum mathematics. Whenever the mathematics has been created or developed, the concept of mathematics has been developed within you, then you can think about how these mathematics can be converted to computing. It's look like first creating transistor, then the concept of 0 and 1, that is Boolean algebra, and then you are writing a program. It's very simple. That means you have to know about very basic of PN junction diode, or you can think about transistor, and then whenever you know the working principle of it, because you don't have quantum computer, or you don't have, whenever you are studying about computer science, you are not creating diode, or you are not creating transistor. You are using transistor. You just know the logic, right? You have to understand the logic. So whenever you have understood it, you just convert it to mathematics. In classical, you are converting it to Boolean mathematics or Boolean algebra. You can convert it to quantum mathematics. You have to understand, and then the next path is to convert that particular mathematics in your programming language. There are different kind of programming language and tools available for quantum, different kind of library. For IBM, it is Qiskit. For Rigetti, it is Pikeweal. For Amazon, it is Bracket. The library name is Bracket. For Microsoft, it is QHash. They have C hash, they have Q hash, and that's it. There are different kind of, and they are also they all programming libraries are also interchangeable. So if you can start through one, then you can also convert other codes to your applications. No issue.
So you are saying opportunities will be there for computer science student also if someone goes through this process.
Yeah. I am also a computer science student. Actually, I am a mathematics student in graduation. Then I have completed my two masters in computer science. One is computer application, another is master of engineering in computer science and engineering from public university. So the thing is, I am also a computer science student. After that, I have jumped into quantum, say 10 years back, 11 years back.
Thank you, sir.
So,
Sir,
so
am I
how-
audible?
Yes.
Yes.
Okay. Sir, I just wanted to know, how does this quantum channel work? I mean, what is the difference between classical channel and quantum channel?
Channel means, okay, it is just about photonic channel. Classical channel means whatever the bus you have. Actually, whatever for communication you have bus, right? And whatever
Yes,
we are using in LAN, they are also bus. Nothing else. They are the other variation of bus. So in case of quantum, this bus is basically called as quantum channel, and they are photonic channel. Photonic channel means you know fiber optics. They are dark
yes,
fiber
sir.
optics where photons or electrons can run from or go from one point to another. It's a simple thing. These are the photonic channel or quantum channel or electronic channel. You can, it is not electronic channel, photonic channel or quantum channel, or you can say it's a ionic channel from one point to other point. Ion or photon or say quantum dot or say superconducting device can run from one point to another point.
Okay, sir.
And in
So
classical,
could
it's
you
called
suggest?
electronic channel. Yeah.
Okay. So could you suggest some books or text materials for cryptography and quantum cryptography and its mathematics?
Quantum cryptography, you don't have, you cannot have a very good book. But yes, for basics of quantum, I will share a particular research thesis from University of Leeds. I have a colleague over there who's known as Lovett. I will share that his research thesis to all of you. You can go through it. You can find a lot of thing in quantum over there. At least basics of quantum. I think
Thank
it
you,
is
sir.
in 2009. Yeah. I will share with Sam about it.
Okay, so thank you, sir. So just I'll request you to share your PPT and whatever you said, the materials. So I'll be preparing a Google Drive so everybody can access that.
Yeah, I will share my PPT and that particular thesis from where a student can start their quantum journey in a technical level.
Okay. Okay, sir. Thank you. Thank you for giving your valuable time. Hopefully, we'll be meeting very soon because I am trying to contact Amlan sir for forming a group in this particular area.
Okay.
Okay. Thank you, sir.
Professor Chakraborty was there in the last month, I think. We have Indo-Australian collaboration on quantum and cyber security over there in Delhi.
Okay.
Chakraborty was there as a guest. I was also a speaker over there. So I have met him last month.
Okay.
I met him last month. But otherwise, I generally communicate with phone and Google Meet. That's it.
Yes. So thank you, sir. Take care of your health.
Yes, it is not about my health because it is about the weather. Because the cold wave warning was there for the last 3 days, and yesterday night it was 5 degree. The temperature was 5 degree.
Yes.
And for me, like who is basically brought up in Bengal and working in South India as well as European Union, it is quite difficult to accommodate with this northwestern Indian cold. It's very rough and very cold and very dry.
Right. Okay, sir. Thank you.
Thank you very much.
So participants, we had a great event, a great session today. And before that also, the first session was great. So I think you have earned wealth actually in that sense, like the new technology, whatever you are learning, that will be a wealth for you. And you can explore all the things, whatever you are learning over here. So best wishes. And today we end up the session for today only. So tomorrow we are having 2 more sessions. So today, bye bye. Thank you.
Thank you, everyone. Thank you.
Thank you, sir.